Okay, let me try to answer these true-false questions. And the first question, this is basically we are asking if you add a closed list in essence while keeping, if you're making depth first search complete, you're trying to do that by refusing to expand node that corresponds to previously expanded state, and then you're maintaining a closed list. So that basically ensures that the closed list will be exponentially large. So basically the answer here is false, because we lose the all important space efficiency of DFS. Okay, so that's the basic idea. A lot of you essentially said, well, yes, it's a graph search, and so it will at least avoid expanding the nodes. But really, there are like two issues. One, of course, is the space efficiency problem. And secondly, in at least some pathological cases, actually checking whether a node has been expanded or not involves duplicate checking, and that can be costly too. So whatever time improvements can be eaten by the duplicate check losses. But really, main thing that I was hoping for is for you to realize that putting the things on closed list will definitely let you lose all the linear memory characteristics of depth first search. Now for the second one, here all we are looking for is to realize that A star search expands all nodes with f value definitely less than, strictly less than f star, and some nodes with f equal to f star. That's the basic point that we are looking for. And so since you are saying the optimal goal is depth 12, and we are assuming that uniform search tree where all operators have uniform unit cost, that basically means your f star is 12. That means any node such that fn is less than 12 will be expanded, and so every node of depth equal to or less than 6 will have g of n equal to 6 plus h of n, which will be guaranteed to be less than 5. So this would be equal to 11, or it will be still less than 12. So it is true because those nodes will have a value less than f star, which is 12. Okay, something of that kind is what we are looking for. Now for the third one, essentially I was just hoping that you'll see it's an extremely silly idea to do iterative deepening. It's an extremely silly idea to do iterative deepening depth first search when all the goals are at the very bottom level, because in that case, essentially what happens is IDDFS is looking at all these levels repeatedly, first like this, then like that, then like that, then like that, repeatedly before it comes to this last level. And so essentially DFS is way better for these kinds of problems than IDDFS. So here the answer is false, because IDDFS does unnecessary redundant work. As an aside, it turns out that as an aside, it turns out that for problems called CSP problems, which we didn't talk about, but I might mention later on, will have solutions. All solutions would be level n. CSP problems with n variables will have solutions at depth n. And so in CSP, we only use DFS. Okay, so that's sort of an interesting point to know. Okay, so but anyway, this is all we really wanted. Okay, now for the fourth question, A star search. This actually I wound up discussing this at length for this problem. I wound up discussing it at length in the context of the review lecture 2, I mean the review session 2. In essence, the one difference is, it's basically what we are looking for is the answer is false, because A star still maintains a search tree while hill climbing just keeps track of current node. So what that means essentially is that in fact A star search can actually take exponential space in these kinds of problems, whereas hill climbing will always take O1 space. So that means O1 space compared to possibly exponential. Of course, the good thing is that A star will be guaranteed to terminate on finite graphs, but hill climbing won't. Okay, so that's the other thing about the hill climbing versus A star search. We actually talked about this. And the bug problem, what we are looking at is that for the bug problem, what we are looking at is that basically the heuristic for the bug problem, when the bug is blind, would involve, for example, taking something like the max distance possible to the goal, and that won't be admissible for when the bug has sight. So again, the answer here is false, because the optimal path for the blind bug may be, remember it's only needs to be maybe costlier than the optimal path for the sighted bug. So the heuristics for the blind bug won't be admissible for the sighted bug, but on the other hand, heuristics for the sighted bug would be admissible for the blind bug. So vice versa does hold. Okay.